Lab 2, Motion of a Falling Object. This lab is about observing and analyzing the motion of a falling object and discussing the role of net force and Newton's second law of motion in this process, as well as discussing how a net force is the sum of its many components. A piece of paper was chosen as the object because of its light mass and relative standardization, which made obtaining its mass and dimensions extremely easy. Here we'll take a closer look at the tracker analysis of the falling object. The origin is set at the initial position of the paper ball, and the axes are set so that the paper ball falls in the negative y direction. The graph indicates to us that the velocity of the ball is changing in a non-constant manner, which means that both an acceleration and a net force are present. As we can see from Newton's second law, in order for the final velocity of an object to be different from the initial velocity, there must be a non-zero net force present, or else the final velocity will be equal to the initial velocity. When the paper ball falls, there are two forces acting on it, the force of gravity, which points downward toward the floor, and the drag force, which points away from the force of gravity. Here we look at the Python code for our computational model. In this picture, we are setting some of the basic attributes of the ball and the initial conditions of the system. The mass of the paper ball is 0.0045 kilograms, and its initial position, velocity, and time are all 0 because we're dropping the ball from rest. Delta t, or the time step, is 0.033 to match the time step of our tracker video, and gravity is set to 9.8 meters per second squared, the constant gravity of Earth. The j-hat, which is the unit vector for the y-axis, is 0, 1, 0. For this lab, we are going to be looking at two computational models, one which accounts for the effect of drag and one which does not. This first picture is a picture of the computational model code that does not account for drag. So in order to calculate the net force for this model, we multiply the ball's mass times gravity, 9.8 meters per second squared times 0.0045 kilograms, the mass of the paper ball. We multiply this by j-hat, the unit vector for the y-axis, to indicate to the model that our ball will be moving in a y direction. We also want to indicate that the force of gravity is negative, so we multiply this entire expression by -1. This code is for our second computational model, which accounts for the presence of drag. The b constant is calculated to be -0.07. This was calculated using trial and error with our observed data from the tracker video. Other changes made to the code include adding a drag force to the net force. The drag force was calculated using the formula -b times the magnitude of the ball's velocity squared times j-hat. The ball's velocity was not used directly because it is in vector form, and we only want a number to multiply by the j-hat vector, which is only in the y direction. This line plot shows us a comparison between our three sets of data points obtained from our three different models. One set, the blue line, represents the data points from the tracker software. The orange line represents the computational model that used a calculation without drag, and the white line, or the silver line, represents the computational model that used force with drag. We can see right away that the model without drag differs greatly from both the tracker software points and the model with drag. This shows us that not accounting for the force of drag can lead to a seriously inaccurate estimate of the final position of the object. The model that accounts for the force of drag, however, is much closer to the correct points obtained from our observed data. This shows us that accounting for the force of drag can lead to more accurate results. Terminal velocity is the point at which the drag force is equal to the gravity. When it comes to which of the computational models predicts a terminal velocity, in my opinion, it is the model that includes drag, because the model that does not even include drag will clearly find it impossible to find a time where drag force is equal to gravity in an accurate manner. This graph was obtained using the same code for the computational models as before, with one exception. We changed the ball's initial velocity to a non-zero negative quantity to show that it is already falling downwards. In this case, we can see that the graph is much more linear. This shows us that the object is far closer to falling at terminal velocity because as the object is falling, the drag force increases as the object speeds up. This will eventually lead to a point where drag force and gravity are equal, and it is for this reason that an object already falling reaches its terminal velocity faster. However, it should be noted that although terminal velocity is reached faster in the case of an object that is already falling, it will remain the same and not be a different quantity simply because the things that are used to calculate terminal velocity are constants, such as the object's mass, density, and shape.